All right, let's talk quantum. But forget the super complex, headache-inducing math for a minute. I want you to think of it like this. We've just been handed a brand new toolkit, and the tools inside, they're weird. They don't follow the rules we're used to. But these strange, powerful new rules are exactly what we're using to build the next technological revolution. So, let's open up this box and see what's inside.
So, to really get this, you have to imagine two completely different sets of rules for how the universe works. First, there's our world, right? The one we see and touch every day. It's predictable, it's certain, you drop your keys, they fall. Simple. But then there's the quantum world. Down at the tiniest scales, everything we think of as normal gets thrown out the window. It's all about probabilities and just pure strangeness. It's a world that doesn't play by the rules we know.
And understanding that weirdness is the key. I mean, if we want to get how things like quantum computers or truly unhackable networks are even possible, we've got to start with the basics. We have to understand this whole new physics they're built on. And it all boils down to one single fundamental building block.
And that building block is called the qubit. Now, you know how all of our current tech, your phone, your laptop, runs on bits, right? They're just tiny switches, either a 0 or a 1, on or off. Super simple. Well, the qubit, it just laughs at that rule. It can be a 0 or it can be a 1. Or, and this is the mind-bending part, it can be both at the exact same time.
So, that ability to be in multiple states at once, that's our very first tool from the quantum toolkit. It's a principle called superposition. And trust me, this isn't just some neat party trick. This is a complete game changer. It's the power of and instead of or, and it fundamentally changes what's even possible to compute.
Okay, here's the best way to picture it. A regular computer bit is like a simple light switch. It's either on or it's off. That's it. A qubit, because of superposition, is more like a dimmer switch. You know, it can be fully off, fully on, or it can be any shade of brightness in between, holding all those values at once. It's not just black and white, it's the entire grayscale.
So who cares, right? A dimmer switch? Big deal. Well, here's why it's a huge deal. That dimmer switch ability means a quantum computer can process a vast amount of information all at the same time. Think about it. Your computer has to check answers one by one by one. A quantum computer, because of superposition, can basically look at all the possible answers simultaneously. This is where you get those insane exponential speedups for solving really hard problems. And it's not just for computing. This is also how we can build sensors that are sensitive enough to measure tiny changes in gravity or time itself.
Okay, so that's tool number one. Pretty cool. But if you thought that was weird, hold on. The next couple of tools in our kit are where things go from strange to, well, just plain spooky. We're talking about ghostly links between particles and things that can literally jump through solid walls.
First up, entanglement. Get this. You can link two particles together in this special quantum way. And from that moment on, they are connected. What happens to one instantly influences the other. And I mean instantly. It doesn't matter if they're a millimeter apart or on opposite sides of the universe. It's no wonder Einstein himself called it spooky action at a distance. It just shouldn't be possible according to our normal rules, but it is.
And the way it works is on the surface kind of simple. Step 1, you link up two particles. Step 2, you separate them. Let's say you send one to London and one to Tokyo. Step 3, you measure the particle in London and find out its spin is, say, up. Well, bam! Step 4, you instantly know, without a doubt, that the particle in Tokyo has a spin of down. That perfect connection, that instant knowledge, is the bedrock for building communication systems that are theoretically impossible to hack.
All right, on to our third major tool. And for this one, I have a question for you. Picture this. You've got a tennis ball and you've got a solid brick wall. If you throw the ball at the wall, can it just pop out on the other side? No, of course not. That's ridiculous. It doesn't have nearly enough energy. But what if we swap that tennis ball for a tiny quantum particle?
Yeah, in the quantum world it can. And it does. It's called quantum tunneling. See, in quantum physics, a particle's location isn't a sure thing. It's more like a cloud of possibilities. And there's a tiny, but very real, statistical chance that part of that cloud is already on the other side of the barrier. So, poof, it just appears there. And this isn't just some wild theory. It's a real phenomenon we absolutely rely on to build crucial parts for quantum computers.
Okay, so let's recap our toolkit. We've got superposition, the power of and. We've got entanglement, that spooky long-distance connection. And we have tunneling,
particles that can walk through walls. These are some seriously powerful tools, but like any advanced piece of equipment, it comes with a very weird instruction manual, and there is one massive catch you have to know about. So let's go back to that amazing qubit for a second. It's in superposition, right? It's humming along, holding all these possibilities at once, the 0, the 1, and everything in between. It's doing its complex quantum calculation in this hidden, secret world of probabilities.
And then you look at it. The second you try to measure it to get the answer, the whole beautiful superposition just collapses. It's forced to pick a side. It becomes either a plain old 0 or a plain old 1. All that quantum richness is gone. Now, this measurement collapse is a massive headache for scientists building these things for sure. But here's the cool part. It's also a feature. It's the whole reason quantum communication is so secure. If a spy tries to intercept your message, the very act of them looking at it collapses the system and you know immediately that you've got an intruder. Pretty clever, right?
So that begs the question, right? How on earth do you work with these things if you can't even look at them? Well, the answer is math. Really, really specific math. Think of it as the programming language for the quantum realm. You don't need to know what a wave function or a Hilbert space is. Just know that these are the tools, the lines of code, that let scientists carefully manipulate the qubits without looking at them and destroying the calculation. This is how they run powerful programs like algorithms designed to crack today's toughest encryption. Okay, so that's the theory, that's the quantum rulebook. But I want to be super clear, this isn't just a bunch of ideas on a blackboard anymore. This stuff is real. People are in labs right now, turning these bizarre principles into actual physical technology. So let's take a look at how they're actually building the quantum future.
And what's so wild is that there isn't just one way to do it. There's this incredible race going on with all these different approaches. You have teams building qubits out of tiny metal circuits, but they have to be cooled to temperatures colder than deep space. You have other teams using powerful lasers to trap and hold single individual atoms in place. And others are using single particles of light, photons. The physical hardware is totally different, but they all run on the exact same weird quantum rules we've been talking about. So let's put it all together in a final summary of our toolkit. Tool 1, superposition. That's the power of being a 0 and a 1, and it's our key to massive computing power. Tool 2, entanglement, the spooky link that gives us truly secure communication. Tool 3, tunneling, the ghostly leap that lets us actually build the circuits. And finally, the rule of measurement, the fact that looking at something changes it, which is both a bug and a feature, giving us even more security. That's the whole shebang. These are the foundations of the quantum revolution.
Look, the bottom line is this. Quantum mechanics isn't just some dusty chapter in a physics book anymore. These are real tools right now being used to build a completely new kind of technology. The toolkit is open on the workbench, the blueprints are being drawn. The only real question left is, now that we have these incredible, world-changing tools, what are we going to build with them?